Our next speaker is Dr. Teng Li, the Keystone Professor in the Clark School of Engineering at the University of Maryland College Park, where he directs the Laboratory for Advanced Sustainable Materials and Technology.
Thank you. Thank you, everyone, and thanks, Bing, for organizing this great conference again, and good to be here to see old friends and meet new friends. I'm going to talk about fatigue failure of densified wood. Did this work? This one. The work I'm going to... What's this? I'm going to present as a teamwork with the colleagues now here in Yale, being for so many years of collaboration. And back in Maryland, Wooly, Bill, Bo, and Chongyu, and also in Vanwood, Yu Jiaqi is here, and also Amy. Okay, so anybody from Minneapolis? Okay, so this is a map of Minneapolis. This is the downtown Minneapolis, and there are two bridges here, very close to downtown. And you see that over there, it's across the Mississippi River. Okay. The major bridge is this highlighted in red. As you see the satellite image over there, it's a 8-lane interstate highway. There is another smaller bridge, 10th Avenue Bridge on the side. Okay. Imagine how close to the big city and how many lanes over there. I'm going to show you a surveillance video camera footage back in 2007, August 1st, Tuesday, 6 p.m. Very typical summer rush hour. Okay. On average, there were more than 100 cars running on Interstate 35W bridge. As you see over there, the greenish, the truss structure is the I-35W bridge, and the archy structure over there is the smaller bridge. Okay, so this is what's happening at that time. The video is slightly slower than real time. It's about less than 2 times. Hopefully the video plays. Okay. This is what happened at that time. The actual happening is slightly faster than this. Okay. Happened in maybe 10 seconds. The lady is making phone calls, and she later on walks back and forth. Okay, imagine more than 100 cars driving through this bridge at the rush hour. This is the aerial image from another side. So now you see the collapsed Interstate 35W bridge, and the 10th Avenue bridge is still there. And that's the location of the surveillance camera. So that's what you see, that in front you will see the Interstate 35W bridge. A major collapse of this happened in a few seconds at the rush hour. So that leads to 13 people died of this and more than 140 people injured. Okay. Of course, engineers looked into the reasons why this collapsed during the rush hour with nearly no signs of this. And a lot of data available for investigation. And this actually is one of the health monitoring image of the bridge. This is the gusset plate. You see that it's bowing, or mechanically we call it the buckling of the gusset plate. Look at the time, 2003. This happened a few years before that, and people said, okay, it's okay. And all of a sudden, after another 4 years at a collapse, unfortunately. Okay. take-home message, two take-home messages. First, metal fatigues, okay, under cyclic loading. These bridges are built in around 1960s, like most of the bridges in this country, major bridges, interstate highways. We know that it's really hard to fracture metal in static loading, but under cyclic loading, they fatigue and fail at a much lower strength. Second take-home message, more crucially, is as you notice from the video, the fatigue failure of metals is catastrophic. And in a more brittle manner, right? It happens all of a sudden. But if you ever done the tensile failure of a steel bar in the lab, it elongates tens of percent at a very gradual way. It's not catastrophic, even though we know that metal are ductile, which is definitely not desirable, right? Of course, as engineers, we try to resolve the issue here. First, can we eliminate fatigue? Very challenging. Almost everything fatigue, us included, right? It's very hard to fight fatigue over aging. So if you cannot eliminate fatigue, then next question you ask is, can you make fatigue failure non-catastrophic? So therefore, the tragic event like this won't happen again, right? So that is the motivation of this piece of research. We will try to come up with some designs to achieve the non-catastrophic fatigue if we cannot eliminate fatigue. Of course, we need to do a fatigue test. This is the fatigue tester we used. It's a rotational fatigue tester. So you see the two holders over there, and the sample over there with the saddle. It's actually like a cylindrical shape, but with a thinner cross section over there. That is the sample we're testing the fatigue behavior. It's held by two holders over there, and this cone shape one extended to this end. And you see a ball bearing over there. We hand weight here. So basically, you are bending the whole thing. And meanwhile, the whole thing is rotating at high speed. So when you put the weight at this end, you're bending this sample in this way. So it is under tension here and compression here. When they rotate half, then the originally under tension now is under compression. So this is a fully reversed cyclic testing. And we ran this overnight for a very long time until it tells us that fatigue failure occurs. Okay. The first thing we test is metal. This is typical aluminum. And you see that that is the original shape of the sample. The two cylindrical part is inside the holder, and the thinner section over there is the part we want to control where it occurs for the failure. And after the fatigue failure, as you can see that it breaks into pieces, two pieces, right? And if you look at the cross section of the fracture, the failure cross section, you will see the very typical metal fatigue, and the outer side, the darker part, and the shiny part is the fatigue crack is propagating slowly over cycles, and then eventually the more grayer intersection of the cross section over there is the final catastrophic breaking of the whole cross section. Okay. We've done this for natural wood as well. So this very similar phenomenon, same dimension of the samples, natural wood, and failed by fatigue, and the fatigue failure is catastrophic as well. It breaks into two parts all of a sudden, and you can see the cross sections over there because this is anisotropic, and then you start to see those wood fibers. So here the wood fiber is along the length direction of the sample. Okay. Now we also did the densified wood following the procedure demonstrated in Nature paper in 2018, and the same dimension of the sample. This is densified wood. And after the fatigue failure, when the machine tells us the fatigue failure happens, didn't break into two parts. So it looks like almost the same thing, but if you look carefully at the thinner section, you start to see cracks over there. But the failure is not catastrophic, okay? So this is the non-catastrophic nature of the failure, fatigue failure of densified wood. And as you can see that this is indeed the highly desirable feature if you want to use this for structural applications, if you cannot eliminate fatigue failure. Okay. And this is the typical SN curve if you're familiar with the fatigue mechanics. So the y-axis is the fatigue strength. So at what level of stress it failed by fatigue. The x-axis is how many cycles of the loading when it fatigue failed. Okay, so it typically has this decreasing slope, and note that the y-axis is linear, the x-axis is logarithmic. So the green line is the aluminum we did, is a typical aluminum fatigue behavior, and notice that the number of cycles is getting to millions, tens of millions, some hundreds of millions cycles, and it's really more challenging to get more data point later on. Okay, so the darker green line over there in the bottom is the natural wood. Okay, it does fatigue, and it typically fails by fatigue less than 1 million cycles, and the fatigue strength is around 50, range from a few tens to less than 100, sometimes more likely is 70 megapascal. And also you notice that the decreasing trend is that if you reduce the load, the cyclic load, you can elongate the life of the sample. Okay. Now the middle blue lines are the data points from the densified wood. As you can see that it follows the decreasing trend similarly, but it has a higher fatigue strength than natural wood. Okay. Of course, we want to know why the densified wood doesn't fatigue failed in a catastrophic manner. For that, we did the CT scanning of the densified wood sample. This is the sample before the test. So basically, CT scanning lets you see what's really inside, because we don't want to break the sample because that will introduce unnecessary damage to the sample. As you can see that the scanning from, this is the lens direction, this is like the cylinder in this way, you scan in this direction, you see everywhere in the cross-section, you don't really see any damage of this. This is the before the fatigue test. It shows that the sample we made is in good quality. Okay. So this is after the failure, fatigue failure. Remember, it remained as one piece. We put it into the CT scanning. Now, you roughly start to see the surface crack as a shade over there. When we run through the scanning, you will see the differences here. That's a surface crack. Actually, it got into the cross-section. But later on, at the another side, the back of the scanning, the crack is not running through the whole cross-section. Roughly speaking, there was a quarter of the cross-section did not really fail or fracture when the fatigue failure occurs. And that's why it's holding together, because densified wood or compressed wood is so strong that even with a quarter of the unfractured cross-section, it remains as one piece. This is a snapshot of the scanning, give you a direct comparison that before the fatigue failure, everything looks perfect. After the fatigue failure, you do see the surface crack start to propagate from the surface, just like the metal samples. It's getting into the cross-section, but as you can see that about a quarter of the cross-section are not failed. Okay. And these are the top rows are the SEM scanning of the natural wood cross-section view. You see all the channels and the voids and the side view of the wood fibers. And after densification, that you see that it's nearly almost all those voids and the openings are gone. The density is very similar to what Lars reported, the 1.25, 1.3, and that essentially eliminated all the nearly all the defects over there and really increased the interactions among the wood fibers. So then that leads to the strong bonding and also leave certain cross-section area of the densified wood sample not filled by the fatigue failure. Okay, so of course, doing CT scanning is time-consuming and also expensive. So we also did the try to address the issue to have the simulation-assisted assessment of the fatigue failure of densified wood. That's the tester we have over there, and that's what we set up in a simulation. That in the unfatigued or the untested sample, we benchmark the simulation model with the experiment over there. So for the aluminum and for the densified wood, it agrees with the green one is the simulation prediction, dark blue one is the experiment result. It agrees quite well. And the large variation of the densified wood tells you that wood is a natural material. The scattering definitely is higher than the aluminum engineering material and more isotropic. Yeah. It's a bending. So as you can see, this is like a cantilever beam. This end is fixed and we hand a weight at this end. The whole thing is under bending and then it's rotating. That's how we tested the fatigue. And then if you have the fatigue damage, as we show here is, if you have more, when x-axis increases, value increases means more damage to the cross-section, then the deflection increases because it becomes weaker, right? So the simulation is in the red, the green line, and it capture well with the shade, the blue shade here, which is the experimental measurement of all the samples we tested. So this means that if you can run the simulation and also test the deflection of the unfatigued superwood sample, we can estimate how much it damaged along the cross section without cutting it. Okay, so this is a side note. Summary. The superwood does fatigue. However, it fatigues in a non-catastrophic manner, which is a highly desirable feature of the structural applications. And scan this to download the paper. Thanks for your attention.
Complete the kind of fade and the non-catastrophic, I think it is non-lethal failure.
Yeah.
How do you define the failure?
Yeah. So this is the wood. Let me see. Go back. Okay. So for the fatigue tester, we have a sensor to monitoring the wobbling deflection of the sample. Because we run this over a very long time. There were certain times, like during the night, nobody is there. So when the wobbling displacement of the sample exceed the threshold, it cuts off the tester to protect everything. Otherwise, it flies everywhere. So that also defines the fatigue failure. So basically, the structure is not stable anymore, and that tells you that you should actually stop and unload this. So in the same definition of the fatigue failure, aluminum, natural wood just failed catastrophic. It happened during the night, then the next morning we see, oh, it broke into two pieces, and we need to look back into the historical data when it happened. But for the densified wood, when it started wobbling like crazy, it stopped, it remained as one piece.
Control by displacement or movement. So have you looked into the residual strength? Let's say when you call it fatigue, how much residual has
residual strength?
Yeah.
We didn't measure that, but we can do that because if you look at the unfailed sample, well, not failed. It's failed by fatigue, but like this one, if there were any residual strain, it's quite local. The dimension of this doesn't really change too much, and the diameter almost. By looking at this, if I don't label those, you won't be able to tell the difference of these two. By really carefully looking at the cross section, you start to see, oh, these are the crack. Then we did the CT scanning to review. Oh, actually, it happened occur 3/4 of the cross section, but not the whole cross section, and that's why it's non-catastrophic.
Structural engineering have still not broken the two parts. It's nice to know how much strength you still have, whether it still can hold up the, let's say, the bridge, right?
Oh, yeah. We didn't really want to keep the sample. Of course, we have multiple samples. We probably can do it. Yeah. That's a very good question.
But we should.
Yeah, so we can chat later.